rails, the ball screws. Hey, what's going on, guys? I'm going to explain to you how I built this CNC machine, how I came up with everything. I drew it up in CAD program in Fusion 360 first, and I used a lot of the online libraries for Fusion 360 just to, you know, for the linear rails, the ball screws, but everything else I drew up in CAD myself. We're going to start from top to bottom. I'm running a NEMA 34 8.2 Newton meter motor in the back with a 1-to-1 drive system on an 1805 ball screw. The linear rails for the x-axis / z-axis are x-axis, z-axis are HGH or HGR 20s with the I guess normal flanged bearing blocks. For the x-axis and the two y-axis motors, there are NEMA 34s 4.8 Newton meters. And the only thing that's really aluminum on this machine is the x-axis, z-axis plate with the aluminum tank for the water-cooled spindle. That is a 1.5 kilowatt, yeah, so it's like a 2 horsepower motor. The x-axis gantry is 2 profiles welded together. I believe they're 60 by 60. No, they're 80 by 80. I couldn't find a rectangle profile that matched what I needed, so I had to weld 2 of them together to get what I needed. The arms themselves are 20 by 80, 4 millimeters thick. The table is 40 by 80, 3 millimeters thick. And the cutting is 60 centimeters, so like, I don't know how much in inches anymore, holy crap. 60 centimeters by 900. The aluminum tank obviously is for the water-cooled spindle. The legs on the machine is a square profile, 80 by 80, 2 millimeters thick with supports at the bottom, are 30 by 80 on all 4 sides. This table, this table is really sturdy, I had no issues so far other than trying to line up the arms for the drive system. That was probably the hardest thing to do because even though you can always place your linear ball screw or your ball screws just right, sometimes it can be off, and in my case it was off. So what I did was I drew a line on here on my wood stop, and I just brought down the bit and just went from one corner to one corner and see how far it was off, and I just adjusted one side and redid it at least twice just to, you know, verify that the machine was indeed running parallel with the table. Same thing with the y-axis, did the same exact thing. I'm going to show you a little bit closer of the electronics, the machine itself. Yeah, so let's get to it. So here's that 1-to-1 drive system for the NEMA 34s. Like I said, this was a 4.8 Newton meters. The Z-axis plate, or the X-axis plate itself, is 500 millimeters long by 200 millimeters wide. Same thing with the Z-axis plate is 200 millimeters by 300 millimeters. Then you got the water-cooled spindle right here. Running some coolant / water in this thing. I made this dust shoe, which I haven't been using when I do the videos. Drilled out the profiles for these wood clamps here. They work really great. Here's that water-cooled tank. So yeah, this machine is still a work in progress. I mean, obviously you would never have your cable running out to the front like this for the spindle. It should be going to the back. But right now I'm still working on the inverter, which I'm trying to control it with Mach 3 through my controller. And in here, it just, they don't have the same exact things as a real Hyundai inverter for the stepper motors. I went through the whole book and yeah, it just was not there. I mean, I see that S1 inside here is running, is for the spindle, but there's other connections like ACM and DCM that you need to hook up to, which they're not in the book and they're not on here. So it's like a still work in progress. So once I get that figured out, how to run Mach 3 through the inverter for the spindle, then everything will be mounted underneath the table. We'll check out these stepper motor drivers. So I got the XYYZ running to aviation plugs on the side. I got the NVUM controller, 6-axis. It works great. I haven't had an issue. I've read online other people's had issues, but if you follow the instructions that come with the CD, you'll have no issues. And exactly what I did was I deviated from their instructions, which is plainly clear English. You can completely follow it easily. I followed somebody else's and had no luck, and I kind of almost gave up on this controller until I went back through the CD and said, oh wow, all this is valuable information, and stick to you know, what they give you. So on this side I have 2 power plants here. They're 48 volts a piece, 14 amps a piece. They are supplying both the stepper motors themselves, and this is for the controller. This one here is for the controller because the controller runs off at 12 to 32 volts. So I didn't want to take the chance of hooking 48 volts directly up. So this is a step down converter, stepping it down to, yeah, I think 24 volts. And then this one over here is running the water pump. The water pump I have is 5 volts. I think it's like 1 amp or something like that. And that's running the water pump. And here's my switch for the water pump right there. There's my drive system for the Y-axis. You can see the stepper motor here. Why ain't you zooming it? There you go. 8.4 Newton meters. I do have this set up on a 2000 pulse with everything has full amps. What I mean is there's half current and full current. I got all these on full current because the system is steel and it is a lot heavier than aluminum. So the motors have been great. They haven't been heating up at all. Yeah, it works wonderful. And I got this like carpet stuff here for the door sweep, because the linear bearings, they do get dusty and dirty, and you don't want to, even though it has like a rubber seal, even though they got like a rubber, let me zoom in here, even though they got like a rubber seal, you can kind of see it right there, still you don't want to get the fine dust in there that can somehow manage to get in there. With the ball screw itself here, with the ball screw I had to put on a spacers on everything, because inside the ball screw, I don't know if you can see it right there, is 44 millimeters or so. Like I was saying, the ball screw with the ball screw nut housing is 44 millimeters. So for me to get the maximum, or like the minimum, the minimum travel behind the plate and the ball nut, I needed to raise it 15 millimeters aluminum. Spacers, that's the same thing for these ones here. I had to do the same thing on pretty much all the drive systems besides the X-axis. I have a plate just coming off the gantry plate to the out to the X-axis here. But the whole machine works great. Surprisingly, it is very accurate when it comes to XY position, the front and leaning of the motor. I haven't, when I'm doing machining, there are machining marks, but it's very subtle, which I'm very surprised at, because I could have swore when I welded the gantry itself that there was a lift on one side, because I tacked everything together like a welder should, tack, 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 tack. Didn't put too much heat on one side. I evened out the heat, so I would weld here, weld the opposite on the other side, weld here, and then weld on the opposite of this side. So everything turned out great. So why is this here? Why is this here? Why is this space the way it is? Okay, so the reason why I added another 400 millimeters or so, or maybe 300 millimeters. 300 millimeters is because eventually I'm going to build a rotation axis going all the way to the back to the front, so that way I can turn round stock for like legs of tables or something like that, or if I do aluminum profiles, bar stock or something like that, I can cut into the aluminum. That would be like a project for later on down the road. But everything else is running great. I've cut a lot of wood. I did some wood tests. I just did depth tests, seeing what kind of blades, what kind of V-bit blades work. So the CNC name is Steel Knight, and like I said, the reason why I chose that name is because it's pretty much all steel, and it weighs roughly around 220 kilos, so about 420-ish pounds or a little bit more. And then I did, this is V-carving with a 16 millimeter bit, and I just wanted to do a depth test on this here. You can kind of see how deep it got. I did various, like A was 8 millimeters and 5 millimeters, 3 millimeters for C, 10 for D, and 6.6 for E. And then the inlay on top. But these turned out great. I'm not too sure why this was. I'm thinking it had to do with the V-bit itself for some reason. This V-bit I was using from Amazon, it seems very sharp, but I think it was grabbing the wood, and you can see it in a lot of the videos. It was grabbing the wood and like just ripping it off. So it wasn't cutting, it was ripping. So I changed this V-bit to this V-bit, which is I believe it's a 22 by 90 degree, and I did a test last night, and when it was cutting into even the light style wood, what I mean by light is like you got the hardwood and I guess not so hardwood, and it was the light wood definitely had like one or two spots had like raised fur or something like that, or it looked like raised wood when it was cutting. So the other bit was leaving everywhere like